Hi everyone, hi, I'm Jeremiah. I'm well known as Presidomath or Jerry Springer. You can encourage me by kindly subscribing to my YouTube channel. Thank you very much. So today we are starting from here. Now this is what we are going to do, transformation of the beta function. That is the different way we write the beta function, and we are going to be proving them. This is the first form. This is the first one we are going to be looking at. Show that the beta of m comma n is equal to integral from 0 to infinity of s raised to the power of n minus 1 all over 1 plus s raised to the power of n plus n dx, which is also equal to integral from 0 to infinity of s raised to the power of n minus 1 mine all over 1 plus x raised to the power of n plus n dx. And at the end of the day, we are told that else or otherwise, we should also show that the beta of m comma n is equal to 1 over 2 integral from 0 to infinity of x raised to the power of n minus 1 plus s raised to the power of n minus 1 all over 1 plus s raised to the power of n plus n ds. So now this is what we are going to be doing. Now this is the substitution we are going to be using. Let x be equal to 1 plus t. 1 over 1 plus t rather. So I will differentiate this. The s is equal to, by differentiating this, the answer I'm going to obtain will be minus 1 all over 1 plus t all squared, the t. Yes, if you use chain rule, you let u to be 1 plus t, you will get minus 1 over u squared multiplied by 1, which is this. So now this is the substitution we are going to have. The next thing is, what is beta of m comma n? Beta of m comma n will be equal to, don't forget the polynomial definition of the beta function, s raised to the power of n minus 1 minus s raised to the power of n minus 1 dx. This is the definition of the beta function, the polynomial definition of the beta function. So now we are going to find t. Make this the subject of formula here. T will be equal to 1 over x minus 1. That is what t will be. T will be equal to 1 over x minus 1. So when s is 0, when s is 0, t will be infinity. And when s is 1, when s is 0, t will be infinity. And when s is 1, t will be 0. So we substitute into this. I have beta of m comma n to be equal to integral. This one will now be from infinity to 0 of s. S is 1 over 1 plus t raised to the power of n minus 1. Then I have 1 minus 1 over 1 plus t raised to the power of n minus 1. Then ds is minus multiplied by minus 1 over 1 plus t all square dt. That's what I'm going to have. The next thing is, I will swap the integral. When I swap the integral, I take away this negative. So this one will now be the beta of m comma n will be integral from 0 to infinity. This one will be 1 over t plus 1 or 1 plus t raised to the power of m minus 1 multiplied by, if we evaluate what is inside here, this one will give you 1 plus t minus 1 all over 1 plus t, which is t over 1 plus t. So I will have t over 1 plus t raised to the power of n minus 1. I told you we have taken away this negative by swapping the bound. I have multiplied by 1 over 1 plus t all squared. The t, right? So What will happen next is beta of m comma n will be integral from 0 to infinity. Everything at the numerator will be just be t raised to the power of n minus 1 all over. This one will be 1 plus t raised to the power of n minus 1. 1 plus t raised to the power of n minus 1. That is plus n minus 1. Then raised to the power of 2 at the denominator. So raised to the power of 2 dt. That is what we are going to have. The next thing is beta of m comma n will now be integral from 0 to infinity of t raised to the power of n minus 1 all over. This is n plus n. Minus 1 plus 2 will give me 0. So this is 1 plus t raised to the power of n plus n dt. So we are done. We have gotten this. We have proved or we have shown that beta of m comma n can be written this way. That is the first one. Don't forget, from the symmetric property of the beta function. Don't forget. So we have proved with this one. We want to prove this. From the symmetric property of beta function, recall that beta of m comma n is equal to beta of n comma m. So if that is the case, it means that beta of m comma n which is equal to beta of n comma m. This just means swap. Anywhere you see n, put m. Anywhere you see m, put n. That's all. So this one will just be equal to integral from 0 to infinity of t raised to the power of n minus 1 all over 1 plus t raised to the power of n plus n dt. That's all. So we have gotten this one as well. Then lastly, we want to show that beta of m comma n is equal to 1 over 2 integral from 0 to infinity of this. Let me call this 1. Let me call this 1, call this 1, and call this 2. Add it together, 1 plus 2. Equation 1 plus equation 2. Beta of m comma n and beta of m comma n. When you add these two together, you will get 2 beta of m comma n is equal to, by the time you add these two together without wasting time, this is what you are going to get, integral from 0 to infinity of t raised to the power of n minus 1 plus t raised to the power of m minus 1 all over 1 plus t raised to the power of n plus n dt. I've already combined the integral. So because they are the same, like they have the same domain variable and they have the same denominator, so I can take this. In fact, the integral is a linear operator, so that's why I can do this as well. So divide both sides by 2. This one will give me 1 over 2 integral from 0 to infinity of t raised to the power of n minus 1 plus t raised to the power of m minus 1 all over 1 plus t raised to the power of m plus n dt. That is what we are going to have. That is all for the first question. So let's go to the second question. Show that beta of m comma n is equal to integral from 0 to 1 of s raised to the power of m minus 1 plus s raised to the power of m minus 1 all over 1 plus s raised to the power of m plus n ds. So that's all. So this is what we are going to do. I will recall from Form 1. From Form 1, I'll recall from 1. What do I want to recall? Recall that beta of m comma n is equal to the integral from 0 to infinity. From 0 to infinity of t raised to the power of m minus 1 all over 1 plus t raised to the power of m plus n dt. That is the first thing I'm going to do. Now look at what I will do here. We know that integral can be written this way. Integral from 0 to 1 of t raised to the power of m minus 1 all over 1 plus t raised to the power of m plus n dt plus integral from 1 to infinity. Integral from 1 to infinity of t raised to the power of m minus 1 all over 1 plus t raised to the power of m plus n dt. That's what I'm going to obtain in this case. Now let's see what will happen. The next thing that will happen is that so I just need to evaluate this. I need to evaluate integral from 1 to infinity of t raised to the power of m minus 1 all over 1 plus t raised to the power of m plus n. I just need to evaluate this. So in this case, I will let t to be equal to 1 over x. I will let t to be equal to 1 over x. So differentiate the t equal minus 1 over x squared dx. When t is 1, of course in this place, this one means that s equal 1 over t. So when t is 1, what happens? S is 1. And when t is infinity, s will be 0. When t is infinity, s will be 0. So the next thing that will happen is I will evaluate this integral. This one will be the integral here will now give me when it is 1, it's 1. When it is infinity, it's 0 of t. T is 1 over x raised to the power of m minus 1 all over 1 plus t, 1 plus x, that's 1 plus t, that's 1 plus 1 over x raised to the power of m plus n multiplied by the t. The t is minus 1 over x squared dx. That's what I have. So I'll swap the bound so that I will get integral from 0 to 1. When I swap the bound, I will get integral from 0 to 1 of this one will become s raised to the power of 1 minus m, or let's do it this way, 1 over s raised to the power of m minus 1 all over, this one will be s plus 1 over x, this one will be 1 plus x over s raised to the power of n plus n multiplied by 1 over x squared dx. Notice the negative sign is not there because I have changed the bound, I have swapped the bound of the integral. So at the end of the day, to write it well, this one will now be integral from 0 to 1. This is 1 over s raised to the power of m minus 1 multiplied by, this is 1 over this one will be multiplied by s raised to the power of m plus n all over 1 plus s raised to the power of m plus n. This is according to the law of indices. This is 1 over s raised to the power m minus 1 multiplied by 1 over all these things will become this. This one will come up s raised to the power m plus 1 over this multiplied by 1 over s squared dx. So at the end of the day, this one will become integral from 0 to 1. This s will be m plus n. This one will be m plus n minus m plus 1 minus m plus 1, then minus 2 all over 1 plus s raised to the power of n plus n dx. That is what I'm going to have. So the next thing I will get now will be so at the end of the day I have integral from 0 to 1 of m will cancel m, 1 minus 2 will give me minus 1, so that I will be left with integral of s raised to the power of n minus 1 over 1 plus s raised to the power of n plus n ds. And the s is a dummy variable, so I can change it to t so that I can suit that. So I can write integral from 0 to 1 of t raised to the power of n minus 1 all over 1 plus t n plus n dt. Don't forget, I told you s is a dummy variable of the integral. By the time you are done evaluating the integral, your answer or the answer you are going to obtain will not contain t or will not contain s. So at the end of the day, I've showed you that integral from 1 to infinity is exactly this. So come back to this. Beta of m comma n will thus be equal to integral from 0 to 1 of t raised to the power of m minus 1 all over 1 plus t raised to the power of n plus n dt, plus the other one is now this integral from 0 to 1 of t raised to the power of n minus 1 all over 1 plus t raised to the power of n plus n dt, right? So therefore beta function of m comma n will be equal to integral from 0 to 1 of t raised to the power of n minus 1 plus t raised to the power of n minus 1 over 1 plus t raised to the power of n plus n dt. That is how we got the second form, or the form 2 of the beta function. Let's go to the next one without wasting time. Without wasting time, from 3 of the beta function, so for from 3, let's see what will happen here. From 3, show that the beta function of m comma n is equal to a raised to the power of m b raised to the power of n integral of 0 to infinity of s raised to the power of n minus 1 over as plus b raised to the power of m plus n dx. This is the next one we want to prove. This is the next one we want to prove here. So in this case, look at what we are going to do here. Recall from form 1. So actually, you need to know all those from 1, from 2, from 3. You can note it actually. You can note it down so that since I've rubbed it off. So from 1, what does from 1 says? From 1 says that integral, that the beta function of m comma n is equal to integral from 0 to infinity of t raised to the power of n minus 1 all over of t raised to the power of n minus 1, or let me use x raised to the power of n minus 1 all over 1 plus s. Whichever one I'm using is fine. Whichever one I'm using is very okay by me. So all over 1 plus s raised to the power of n plus n ds. So let, in this case, this is the substitution we are going to be using. Let s be equal to at over b. So this is the idea. We want to make this one to resemble something like this. That's the idea behind it. So if I make T the subject of formula now, or no, before I make T the subject, the S will be equal to A over B dt. The S will be equal to A over B dt. So the next thing is so the next thing we are going to be doing here, make S the subject of formula, make T the subject. By the time you make T the subject, you will see that actually T is equal to Bx over A. So it follows that when S is 0, T will be infinity. T will be 0 rather, sorry. When S is 0, T will be 0. When S is infinity, T will also be infinity. When S is infinity, T will also be infinity as well. Do you get my point? So now, I will now substitute into this. It means that the beta of m comma n will be equal to the integral from 0 to infinity of S. S is A over T, AT over B, AT over B raised to the power of m minus 1 all over 1 plus AT over B raised to the power of m plus n multiplied by the x. The x is A over B dt. A over B dt. So at the end of the day, this one will be equal to integral from 0 to infinity. This will be A over B raised to the power of m minus 1. That is what we are going to have first. Then multiply by T raised to the power of m minus 1. Then this one will be 1 over B plus AT all over B raised to the power of m plus n, then multiply by A over B dt. That's what we are going to have. So this will be equal to integral from 0 to infinity. This is A over B raised to the power of m minus 1 multiplied by T m minus 1. Then this one will be B raised to the power of m plus n over AT plus B raised to the power of m plus n multiplied by A over B dt. So to round it off, this one will become integral from 0 to infinity. I will pick only A. A is A raised to the power of m minus 1. Then another A is here, that's plus 1. Then for B, I have B raised to the power of 1 minus m, because this is B raised to the power of minus 1 raised to the power of m minus 1, which will give me 1 minus m. Multiply plus m plus n plus m plus n, then I have minus 1 dt. Then I have this one is still there, Tm minus 1, then 1 over AT plus B raised to the power of m plus n dt. All what I've just done here is just the law of indices. I bring all the A's together and I brought all the B's together. So this one will be integral from 0 to infinity. This is A raised to the power of m only. 1 minus 1 will be out, minus m plus n will also be out. So you have B raised to the power of n as well. Then you have T raised to the power of m minus 1 multiplied by 1 over AT plus B raised to the power of m plus n dt. So To conclude this one will just be equal to a raised to the power of m, b raised to the power of n integral from 0 to infinity of t raised to the power of m minus 1 all over at plus b raised to the power of m plus n dt. And we are through. So beta of m comma n will be equal to a raised to the power of m, b raised to the power of n integral from 0 to infinity. I told you t is a domain variable of the integral. I can change it to x minus 1 all over ax plus b raised to the power of m plus n dx. And that is what we have proved. We want to go to the next form, from 4. Show that integral from 0 to pi over 2 of sine 2n minus 1 theta cos 2n minus 1 theta all over a sine square theta plus b cos square theta, the theta is equal to the beta function of m comma n all over 2 a raised to power m b raised to power n. Or I can bring this 2a raised to power m b raised to power n to this side so that it will just be beta of m comma n. So that is what we want to do. This is the next form we want to prove. Now, I will record from 3. That is where I will start from. I will record from here, from this place, from 3. I have beta of m comma n to be equal to a raised to the power of m b raised to the power of n integral from 0 to infinity of x raised to the power of m minus 1 over as plus b m plus n raised to the power of ds. So this is what I will do. I will let x to be equal to tan square theta, because tan square have sine and cos. Tan is sine over cos, and this is what I have there. So I will differentiate this. ds will be equal to sec square theta. So when s is 0, theta will be 0, and when s is infinity, arctan of infinity will be pi over 2. That's 90. So when s is 0, arctan of 0 is 0. Theta will be 0 degrees. And when s is infinity, arctan of infinity is pi over 2, 90 degrees. That's pi over 2. So I will use this. Don't forget, the beta function of m comma n will be equal to a raised to the power of m b raised to the power of n integral from 0 to pi over 2 of s. But s is tan square theta raised to the power of m minus 1 all over a. S is tan square theta plus b raised to the power of m plus n dx. The s is sec square. So This is not the derivative of sec square. This one will give me 2 tan theta sec square theta. So it is only when you have tan x that the derivative will be sec square s. So I have tan square s, so it will be 2 tan theta sec square theta. So this one will be multiplied by 2 tan theta sec square theta. Sec square theta the theta. So the next thing that will happen here, a raised to the power of n, b raised to the power of n integral from 0 to pi over 2. This one will be tan 2m minus 2. The power we multiply each other, it will become 2m minus 2, then plus 1. This is plus 1. That is 2m minus 1. So that is tan 2m minus 1 over, this one will still theta, this one will still be a tan square theta plus b raised to the power of n plus n multiplied by 2 sec square theta. So now let's write it out explicitly. Let these two come outside. This one will become 2 a raised to the power of n, b raised to the power of n integral from 0 to pi over 2. Tan is sine over cos, so I have sine theta over cos theta raised to the power of 2m minus 1 multiplied by, this is 1 over, this one is also a sine square theta plus b cos square theta all over cos square theta. So raised to the power of n plus n. Then sec is 1 over cos, obviously. That is multiplied by 1 over cos square theta, the theta. So that is what will happen. 2 raised to the power of a raised to the power n, b raised to the power n integral from 0 to pi over 2. This is sine theta over cos theta raised to the power of 2m minus 1. Then multiplied by this one will become cos theta raised to the power of 2m plus 2n over a sine theta, a sine square theta plus b cos square theta raised to the power of n plus n multiplied by 1 over cos square theta, the theta. So that at the end of the day, by the time I evaluate all this, this will become 2a raised to the power of m, b raised to the power of n integral from 0 to pi over 2 of, now this will be sine 2m minus 1 theta. That is what I have, that's the only sign. Then cos, I have cos, here I have 2n plus 2n, then this one will come up to become plus 1 minus 2m, this one will come up to become minus 2 theta. So all what I have just done here is law of indices as well. So I will now have all over a sine square theta plus b cos square theta raised to the power of n plus n, the theta. So it implies that the beta function of m comma n is equal to 2a raised to the power of n, b raised to the power of n, integral from 0 to pi over 2. This is sine 2m minus 1 theta cos 2n minus 1 theta all over a sine square theta plus b cos square theta raised to the power of n plus n the theta, and that is the answer to this one. Oh, I did not put n plus n, this is n plus n, so that is what I have here. I can just divide both sides by 2 raised to the power of a m bn, so that I will have exactly that. That is, I have b m comma n all over 2a raised to the power of m b raised to the power of n equals integral from pi to pi over 2, from 0 to pi over 2 of sine 2n minus 1 theta cos 2n minus 1 theta all over a sine squared theta plus b cos squared theta raised to the power of n plus n the theta. That is what I am going to have. That is the answer.